So the first graph we're going to explain today is atomic number and ionization energy plotted together. So notice on the x-axis, or the independent axis, we have atomic number. On the y-axis, we have ionization energy in units of eV, electron volts. So let's figure out how to read this. Notice there is no 0, 0 on this graph because there's no element with an atomic number of 0. You have to have a proton in order to have a nucleus, right? So this is our first point right here. That's atomic number 1. So what element is atomic number 1? So this is hydrogen here. And then let's go to atomic number 2 up here. That's helium. So remember we talked about the noble gases do not follow all of the trends, but ionization energy is one that they happen to follow. And let's talk about why. Ionization energy is measured in that I will take an atom. I know what the identity of the atom is going into this, and I'm going to start shooting energy at it. And at some point in time, you're going to increase the amount of energy as you go along, and at some point in time, an electron will fly off. The energy at which that first electron flies off, you've removed the first electron. That's called the first ionization energy. And then you'll keep increasing it, and another electron will come off. That's called the second ionization energy. There's called successive ionization energies, which we'll explain in greater detail next week. So this is the first ionization energy, and if you notice, the noble gases are at the top. This is atomic number 10, so it's neon. Here's 18 for argon. So what's happening to the ionization energy as you go down a family, though? It is decreasing. So after helium, we come to lithium all the way down here, which is what's to be expected. Notice that this is lithium to neon. So this is the second principal energy level represented from lithium to neon. Notice that lithium has the lowest ionization energy. That's because lithium has 1 valence electron. He knows he can't get 7 more to get to 8, so he'll lose his 1 and end up like helium. Remember, all of the elements are working to get to a noble gas configuration. So they will lose or gain electrons in order to have a noble gas configuration. But let's go next to beryllium, which is right here. And then next is boron. Look at this little dip right here. That's called a deviation from the trend, which is okay. And let's talk about the reason why this happens. So when we say deviation from the trend, let's explain it this way. You know now it's the last day of September. It's going into October. It's going to start getting colder out, isn't it? You know that. Does that mean that there won't be a 90-degree day in October? Does not mean that. In general, it's going to get colder, but there are certain days that will be a little bit warmer. I'm going to explain this using electron configurations. So first I'll do beryllium. The complete electron configuration is 1s2, 2s2. The noble gas configuration would have core electron of helium, and then 2s2. It has 2 valence electrons, and they're the 2s2. But watch the box diagram. The box diagram tells us some good information. Remember, I draw one arrow up and one arrow down according to Pauli exclusion principle. Those represent the opposite spins of the electrons. Electrons cannot occupy the same orbital unless they have opposite spins, and that's Pauli exclusion principle. So each orbital is represented by a box, and each orbital can hold a maximum of 2 electrons with opposite spins. Now let's do boron. Just one more electron here in the 2p. The noble gas configuration would be same core of helium, then 2s1, 2p1. I'll do the box diagram over here. So 1 electron up, 1 electron down, and this is the 2p. So what this dip means is that in order to shoot energy at this electron to pull it off, it takes more energy to pull off that doubly occupied 2s electron because the 2s orbital is full and a little more content. It will take you more energy to pull this electron off than the singly occupied 2p. That's the reason for the first dip in the trend. Let's keep going on and talk about the second one, carbon. And then we have nitrogen and oxygen here. That's our second dip. We'll use the electron configurations to explain this also. So nitrogen is 1s2, 2s2, 2p3. Noble gas configuration is as follows. Shows you the 5 valence electrons. Let's do the box diagram. So 1, 2, 3, 4, 5, 6, 7. Notice I gave each orbital 1 electron before I gave anybody 2. And that's due to Hund's rule, because this has a lower energy configuration than if I had them doubled up, because electrons repel each other. Now let's do oxygen. Has the noble gas configuration with helium as the core and its valence electrons, which are 2s, and 4p valence electrons like such. Let's do the box diagram. One, 2, 3, 4. So oxygen has 2 unpaired electrons. And this dip here can be explained by saying this first electron here, it takes less energy to pull off that first doubly occupied p sublevel than the singly occupied p level. So our 2 exceptions come from when that first p electron starts to fill up, and then that 4th p, which will start to double up. So when the guy's standing alone, it takes less energy to pull him off. And when the guy's first trying to double up, it takes more energy to pull him off. So that's where that exception to the trend comes from. What do you think this mess down here is? Here's potassium and calcium, right? What comes after that? Yeah, so that whole row. Now we're talking about our D block or our transition metals. Notice that the trend, not really much to see there, right? And let's talk about why that is, because calcium and potassium are in the 4s sublevel. So the valence electrons are 4s. Then once you go start with scandium through zinc, the 4s, the valence shell is the same for all of the 3D elements. They all have two 4s electrons as their valence shell. Then we're starting to fill the 3D. So that's actually the previous electron shell. Can you see how that doesn't change anything about the valence shell? And that's the reason why the transition metals don't follow that trend. Okay, let's go to the second graph, which is atomic number on the x-axis again, and this time atomic radius. Notice that unit there. Does anybody know what PM stands for? Yes, picometers is PM. So when I was your age, we didn't have to deal with all these super small. I'd never even heard of any of these super small units. Like when we were talking about our wavelengths, we talked about nanometers, which was 1 × 10⁻⁹. Now you're doing picometers. 1 picometer is 1 × 10⁻12 meters. That's super, super, super small, huh? You're also going to be facing some huge units that I never saw before. But you're probably more comfortable with that, those huge units. Like when I got back before smartphones were out and we used to have to buy iPods to listen to music, my first iPod came in kilobytes. Held 100 songs exactly. New song came out, you wanted to put it on your iPod, you had to delete an old song. Just 100 regular songs. Now, think about your cell phones. Store more than that, right? You know what the memory is on your cell phone? Bytes. That's a lot. Especially compared to kilobytes.
I suppose the terabyte out there.
If you have a computer at home and it's fairly new, it's probably in terabytes. Those units never even existed when I was younger. They're just so astronomically huge. So kilo, we talked about, which is 1,000 meters in a kilometer, right? So there's 1,000 bytes in a kilobyte. Mega is 1 × 10⁶. That's about as high up as we went. Okay, let's explain what's going on here, because this can be confusing. Let's find atomic number 10 right here. We're going to find atomic number 10 because it's right on the line here, right? What element is atomic number 10? Neon. Notice there is no point for neon. What that means is the noble gases are not on this graph. And let's see if we can figure out why. So again, what's this mess here? D block transition metals. And then you'll notice D block transition metals. And then you get to this mess. All of a sudden we've got F block in there, right? So the way that they measure atomic radius is they take, remember I drew you a picture of fluorine, where they can take a bonded atom and they measure the distance between the nucleuses, and then they cut it in half. That's what atomic radius. So the reason, if we're going to do that, if we're going to bond all these elements, everybody on the periodic table of the elements, put them in a bond, and then measure the distance between nucleus, Can you see how that excludes the noble gases? Because the noble gases are not going to bond. You're not going to make a bond with helium. So we do know some things about the atomic radius of the noble gases, but we can't measure it that way. So you can't just do something different. When you are doing scientific investigations, your method has to be the same for all of it. Otherwise, you can't relate them to each other. So here's the reason why. So if this is hydrogen and helium's not even on the graph, then what is this one up here? That's lithium. So can you see what's happening to the atomic radius as we go down a family? It is increasing. So let's use potassium, go backwards. This would be where argon was, but there's no point there for a reason. And then previous to argon is chlorine here. So you see from sodium down to chlorine, the atomic radius is decreasing. The reason for that is we're in the third principal energy level. So everybody has the same amount of electron shells from sodium all the way to argon. Everybody's valence electrons are in the third electron shell. But what we're doing is we're increasing the nuclear charge. So we're adding protons to the nucleus. And what that does is it allows the atom to pull its electrons closer. Remember, atoms are mostly empty space. So if you took all the actual electrons and protons in the universe, it's actually a little tiny bit of matter. All the people in the school wouldn't even fill a thimble of actual matter. So we're talking about how close can the atom pull its electrons to the nucleus. And the increased nuclear charge, or Coulombic effect, allows these atoms to pull their electrons closer. So this was supposed to clarify those graphs a little bit before you are looking at them and answering the questions.